Hey everyone, so when we look out into the night sky, we see that there are stars and we see some other bright dots, and ancient people even knew that the stars stay put, but these wanderers, these planets that moved throughout the heavens were different.
Yeah, so it was inevitable that people wanted to know how they moved. And so eventually what would happen is they would start to track these things and their positions in the sky over time.
So there was two types of planets that they knew of. They knew that there were what we call inferior planets that never strayed too far from the sun. They were either there right after sunset or right before sunrise. So Mercury and Venus became our inferior planets.
And there were the outer planets, or the superior planets, which seem to move very slowly and take a long period of time to do their thing. And those are the ones that are outside of the Earth.
And we also see them in the middle of the night. They could be opposite of the sun. They didn't have to be kind of hugging the sun.
That's true.
So like we did in class, we took positions, right ascension declinations for some of the planets, and plotted where they were throughout their orbit. And if you look on this plot, Saturn started in Sagittarius on April 10th of 2018, and then we plotted it for several motions throughout the night sky. I know it makes one full orbit when it returns to Sagittarius.
Right, and in this particular case, it takes about 29 years to make that one orbit.
So it won't be back there until March 31st of 2047.
Amazing.
It's a long orbit. But there is one odd thing we noticed in this orbit. It looks right over here around August 24th of 2031 to March 12th of 2032.
Yeah, it looks as though the planet slows down or even changes direction with respect to the rest of the chart.
And to ancient people, this was a really freaky thing, because to them, the stars were heaven, and you had these wanderers, these gods, wandering through the heavens. If the god is walking backwards, then
something bad is about to happen.
But we have some other reasons why this might happen. We call this motion retrograde motion. We've got two ways to explain retrograde motion. We can get into two little camps here. I'll join the geocentric world, which means that really Earth is special. Earth is at the center of the universe, and everything revolves around us.
Right, well, and then there's the other way of thinking, which is having the sun in the center, or heliocentric. Everything goes around the sun, not around the Earth.
Okay, but from my point of view, I don't feel the Earth moving. I see the sun come up in the east and set in the west. I see the planets do the same thing. I see things revolve around me. I'm not moving.
That's true. I don't think cavemen thought that they were moving either.
But then retrograde is a little tough to explain. So let me show you my model for the geocentric world. So at the time in the geocentric world, you can see most of the world was not mapped yet. People were just starting to write things down, and it made sense that we weren't moving. As I back out, the very closest thing to me is the moon. And the moon, since the moon is round in the heavens, it must be perfect. Circles are perfect, so it went around in this circular pattern. If I walk out a little further, I see that there's Mercury on its own perfect circle. But it's also got this secondary circle that is rotating. And if you notice right now, Mercury looks like it's rotating backwards, stopping, and then going forwards again. Venus even does the same thing. Venus has this epicycle, this tiny circle within its orbit to explain my retrograde motion. Mars just has an even larger epicycle, since it takes longer for that to happen. Same with Saturn and Jupiter. That was the edge of the ancient world of how far we could see.
Well, your arguments are very compelling, but arguments for the heliocentric universe, I think, are even more compelling. In the heliocentric universe, the sun is at the center. As we can see, the planets are going to go around that. If we could look at the motions of these planets, that would also explain how planets move with respect to each other. And as you can see, the closer a planet is, the faster it goes around, and at times it will go past the planet and make that look like the planet is moving backwards with respect to it. As far as in the sky is concerned, if we looked at the sky, that would make the planet move backwards in the sky.
And because you knew that the planets inside, they pass us more often than those outer planets, those superior planets way out here.
Sure. But it still happens, but we just don't happen to see that retrograde motion as often with the planets outside. I still have perfect circular motion, just like the geocentric model, and I have an easier explanation for retrograde.
I think we have a demonstration of that.
We sure do.
In your heliocentric world, the yellow pad is the sun, and you are an outer planet, and I'm an inner planet.
I am a superior planet.
And as I pass you, it looks like you just stopped and then kind of walked backwards. Now as I approach you again, you're walking across the sky normally. As I approach you, you're slowing down and going backwards from my point of view.
Yes, I am. It didn't require me to do any kind of geocentric motion like those things called epicycles, which are circles on circles in these orbits.
And that my model is a little confusing, and your explanation does make sense. When an inner planet passes an outer planet, they'll see retrograde from their point of view. But guess what? My model's more accurate. If you want to know exactly where a planet was in the sky, the geocentric model works.
So how could we make a heliocentric model more accurate? I think we'd have to come up with some other ideas that would make it look more like what was really happening in its surroundings.
And that's where Johannes Kepler came in. He made even better measurements than anyone else did about stars and planets. And again, he did this all without telescopes. The first telescopes were being invented while he was doing his observations. And with his rules, he was able to kind of determine how the solar system works. Another activity you guys did in class was saying that the sun was at Penn Trafford, and we plotted Neptune right there in the middle of Trafford along Route 130, about 6.5 miles from school. With Kepler's rules, we could actually tell you where all the other planets are along that.
We sure could.
So here are Kepler's new rules. First law that he said for planetary motion was that planets don't go in circles, which is really against what we said before. That was the heavens. The heavens were perfect. Circles are perfect. But he said that can't be. These planets must be moving in elliptical orbits, which means more egg-shaped orbits. The sun is not the center focus. The sun is off-center. And sometimes you're at perihelion, which means pretty close to the sun. And sometimes you're at aphelion, which is pretty far away from the sun.
And this would kind of explain why when we look at planets in the sky, they sometimes appear to be changing speed. The second law as far as speed of the planets is that the closer that a planet is to the sun, the faster it's going to move. But because of that, the area at which the planet actually covers with regard to the sun is the same regardless of whether it's at distance or whether it's close. As you can see here, when the planet is far away, a 1 month period, it doesn't move as quickly, but the triangle that it creates with the sun is the same as the 1 month period when the planet is closer.
And of course, we have a little demonstration for you with Mr. Gay sitting on one of our spinny chairs. He's holding two masses out. What's going to happen when you start spinning?
Well, first I'm going to get dizzy. But when I pull my arms in, when the center of mass is tighter, I spin faster. And then I slow down when that center of mass is further out.
So when you pulled those masses in, that's like having the planet very close to the sun.
Yes.
And you spin very, very quickly. And when you opened your arms up, it was like the planet got far away from the sun and started to spin very slowly. So that's how he could justify the elliptical orbits. How can you travel in these weird egg-shaped orbits? Well, you change your speeds at different times of the month. For us in the northern hemisphere, when is summertime?
It's June.
June, yes. Are we closer to the sun or are we further from the sun?
We're actually further from the sun in June.
That is weird.
Yeah,
that is weird. In wintertime, we're actually, in the northern hemisphere, closer to the sun. We'll have to come up with a reason why it's warm in the summer and cold in the winter later. But his last law was the clockwork. This told you the exact time it takes a planet to go around. We said that Saturn went around in about 29 years. Well, with his equation down here, the time squared multiplied by some constant equals the distance from the sun cubed. And that was the average distance, not the aphelion or perihelion distance. And once he knew the time of each planet, like we told you, 29 years, you put that in this equation, and it tells you that that Saturn is about 10 times further away from the sun than Earth.
Which makes it 29-year orbit.
And gives it superior status being outside Earth's orbit. And we did this for all the planets then, and he knew exactly how far away everybody was and how long it takes you to get there, which allowed future astronomers to predict if there's going to be other planets in our solar system.
He's a smart guy.
Smart guy. So know these 3 laws and know how they explain the motion of the planets. We'll talk to you next time.